Today I'm going to talk about user-assisted video reflection removal. So what are video reflections? Videos have become one of the most popular information carriers. Capturing videos is often met with undesired obstructions. One of these obstructions is reflections. The problem we're interested in solving here is reflections in videos. This occurs mainly when you take a video behind a reflective surface, such as a glass barrier, as shown in the figure. Why are we interested in solving this problem? In photography, reflections lead to loss of information in the scene and reduces the video reusability. In self-driving cars, cameras are usually mounted behind a glass barrier, causing reflections and poor understanding of the surrounding environment. Reflections also reduce the accuracy of many computer vision algorithms. So reflection removal can be used as a pre-processing step for many computer vision algorithms. If you have a look at the prior work, most of the prior work is targeted toward this single image reflection removal. For example, one that stands out is the work done by Fan et al. And to extend this work on videos, we can apply it frame by frame. However, this leads to incomplete separation, temporal flickering, color changes, and blurry output of the video. However, the work that is mainly targeted towards video, to our knowledge, there exists only one work about video reflection removal. This work is done by Ajay et al. However, this work only assumes simple non-dynamic motion that's easily distinguished for each layer, so it cannot handle common cases with dynamic complex motion. Here we're going to define our problem. We model video reflections as an addition of two layers, background and reflection. The problem we're interested in is to separate each frame in the video in its two layers. Clearly, there is an infinite number of decompositions. This makes the problem severely ill-posed. To have a general overview of the method we're using here, the key idea is to use motion cues to separate the layers with the help of user assistance. The pipeline of our method is shown in the following figure. We start by estimating the motion of each layer with the help of user assistance. We then utilize the estimated motion to stabilize both layers and provide some initial separation. We then perform optimization process to initially separate the layer on the initially separated layers to provide the final output for each layer. Let's start with user-assisted motion initialization. The objective of it is to estimate the two dominating motion in the video. Here, I'm going to explain the intuition of using motion in layer separation. For example, as shown in the figure, the background and the person have two different motions. When using a k-means clustering algorithms on the long-term tracks in the video, the output classified two different entities, one for the person and one for the background. This means that clustering of these long-term tracks can help us in classifying the objects with different motions. A track here is basically a point, such as a feature, a corner, or an edge, with its position tracked for a certain number of frames. But how does this relate to the problem in videos with reflections? We can also model videos with reflections as containing two layers that have different motions due to the visual parallax. If the reflected object is relatively closer to the camera than the background object, the projected motion on the image plane will be larger than that of the background objects and vice versa. From this observation, we can conclude that both the background and the reflection layer have different motions, so we can classify objects in the background and reflection based on their motion. There are a lot of challenges associated with user-assisted motion initialization. One of them is dead tracks. It occurs when a track identified for a limited number of frames only. And this is a really common problem. That's because due to a collision or obstructions by the other layer. For example, if we look at the snapshots of this video at frame 1 and frame 12, we can see that the helmet of the person was tracked in frame 1. However, this track died at frame 12 because of obstruction from the reflection layer, which is this blurry part. Another problem or challenge associated with user-assisted motion initialization is weak features. Features having low contrast or low color informations are hard to detect by the tracker. color information is essential for the tracker to detect and track a feature. And if there is not enough color information, target tracking is hard or nearly not achievable. For example, if we look at the video here, if we look at the frame at frame 1 and frame 20, we find that the person in the background, shown in the blue and the green squares, doesn't have any tracks associated with him. That's because this person had low color information, so the tracker couldn't detect or track his motion. The next challenge in user-assisted motion visualization is motion clustering. It's a really challenging task. For example, if you look at the video, if we look at the following video taken inside a building behind the window, you can see that the reflection from objects inside the building appearing on the window. If we take a snapshot of the pre-computed tracks before clustering and the clustered tracks using k-means clustering algorithm, before clustering, all the tracks have the same label. They are all blue. After using k-means clustering, the background tracks are classified as the blue tracks and the reflection tracks are classified as the green tracks. We can see that the clustering here is wrong. Most of the buildings, the background, are clustered as green tracks, which means that they are clustered wrongly as belonging to the reflection instead of the background. Due to the challenges described before, the process of accurate motion initialization is difficult. Thus, we propose a method that integrates an intuitive GUI with the process of motion initialization. In the first row, we show the frames in which the user will provide sparse user hints. The first step is to calculate the pre-computed tracks using a tracker based on large displacement optical flow. This is represented in the second row. This is done before any clustering. Then we utilize user hints to cluster these tracks. For example, as shown in the third row, in frame 1, the user marks sparse hints over space to cluster the tracks. The blue belonging to the background and the red belonging to the reflection. The user didn't mark all objects, but it was provided sparsely over space. We propagate these sparse hints to other tracks in the frame through random walk computation. The user also provides these hints sparsely over time. For example, the user here didn't provide tracks in any of the intermediate frames from frame 0 to frame 30. The user only provided the hints in frame 0 and frame 30. So the user provides these hints sparsely over time. And we can see that the pre-computed tracks propagate the labeling information provided by the user to the intermediate frames as shown in the fourth row. This is the result of the motion clustering using user assistance. If we look at the snapshot of the motion clustering using user hints and without user hints using k-means clustering, we can see that the bicycle driver is labeled as belonging to the reflection instead of the background, while user clustering was much more accurate, clustering the bicycle driver as labeled to the background. The next step after clustering is motion stabilization and initial layer separation. After clustering, we already know what tracks belong to the background and what tracks belong to the reflection. This is represented in the warping matrix. A warping matrix represents the motion from one frame to another. So to do the stabilization, we take a sliding window of 10 frames. We multiply the warping matrix from each frame and the first frame. What we basically do is that we warp all the frames on the first frame using the background warping matrices. This results in a window or a warped frames where the background motion is nearly stable. Thus, we can provide initial estimation of the background layer when we use minimum temporal filtering. After having these initial estimations for each frame by passing the window frame by frame, the next step is to do some optimization. Our optimization equation consists of three main parts. The first part is to make sure that the recovered layers satisfy the video compositing model. Here we optimize for PT and RT, which is IT minus PT, which is the background and reflection frame estimations. This is done by minimizing the error between a layer at time t and its warped version at time rho. The warped version, as we can see, is the frame at time rho multiplied by the warping matrix. The second element in our optimization is information we get from prior information. The layer prior imposes some labeling constraints on the separated layers. This can be done by assigning a binary map to which each layer edge belongs to. After warping on the first frame in each sliding window, we're stabilizing the motion of the background, and thus, if we look at the warped gradients, the more stable warped gradients should belong to the background, while the less stable warped gradients should belong to the reflection. MT here is a binary map, and it's calculated by thresholding the alignment errors of these gradients. The last term for optimization is for spatial smoothness over the constructed layers. This is done by minimizing the first order spatial gradient of the background and the reflection layers. For evaluation, we shot and collected many videos, around 156 videos from some of them were indoors, outdoors, during different times of the day, different lighting conditions, and we provided some qualitative results on these natural videos. For quantitative analysis, we need access to the ground truth decompositions. Thus, we generated some synthetic videos using the additive layer compositing model. We basically mixed the background reflection with different mixing parameters, as shown in the figure below. For evaluation, we compare against two different approaches. The first one is the state-of-the-art single image reflection removal done by Fan et al. And we extend it to videos by applying it frame by frame. The second one is the state-of-the-art video reflection removal by Ajay et al. We refer to it as VRR. Let's have a look at the videos, and we are going to dive deeper on the results from the video. Here we can see the difference between our background estimation and the two other methods. We can see that ours provide better separation than most the other methods. The same also for the reflection. The same here happens. We can see that there is some color changes in using the frame by frame reflection removal method. There's also some blurry and incomplete separation using the VRR method. However, our method showed the best separation out of all of them. Here are some more results. Here we can see better separation, and we can see the reflection layer and a person taking a video of the red sign. We can also see the street and the signs and the reflection. And now let's dive to a more qualitative analysis of the previous videos. For example, for this given video, if we look at the snapshot of the separated background and the separated reflection, the two state-of-the-art methods, frame-by-frame reflection removal and video VRR, we can still see that using the frame-by-frame reflection removal, we can still see some color changes. We can also see some reflection artifacts in the separated background layer. Using the VRR method, we also see some reflection artifacts, and we see some unclear recovery of the background layer. However, our approach shows the best separation out of all of them. The same applies to this video. We can see that the input has some reflection artifacts here from the room, from a whiteboard reflected on the glass barrier. We can see that using frame-by-frame reflection removal, we can still see some reflection artifacts, and we still see also some color changes. The same for VRR, we can still see some clear reflection artifacts in the separated background. However, our method showed the best separation out of all of them. For quantitative analysis, we need access to the ground truth decompositions. For example, here we generated a synthetic video, and we took snapshots or results of other methods and ours, and we found that ours had the best separation out of all of them. For example, using frame-by-frame reflection removal, we can still see reflection artifacts and unclear recovery and color changes in the separated background. In using VRR method, we also still see some reflection artifacts. However, our method showed much higher separation and complete recovery of the background layer. To measure this quantitatively, we measure the structure similarity index against the ground truth. For example, if we look at the separated layers, we can see that both of them have less structure similarity index when compared to the ground truth for the background and reflection layer than our method. Our method showed the highest structure similarity index with the ground truth decompositions. In conclusion, in this work, we present a user-assisted method to remove undesired reflection from videos. The method is based on motion cues gathered by sparse user heads. The method is we show quantitative and qualitative results on challenging real and synthetic examples. We also compare against state-of-the-art reflection removal methods, and our results showed improvements in the separation quality than prior work. Thank you.